Hello everyone! Have you ever stopped to think about how the electricity from a giant wind turbine can somehow charge the tiny battery in your phone? Or how a car battery can unleash the power for a high-performance motor? Well, the answer is all around us, in a technology that's so fundamental it's practically invisible. Today, we're going to pull back the curtain on this hidden world. We are talking about power electronics, the essential universal translator for electricity.
So, here's our game plan. First, we're going to unpack the basic problem that makes this whole field necessary. Then, I'll walk you through the 4 foundational circuits. These are the absolute building blocks of all power conversion. And finally, we'll see how these simple blocks build our entire modern world. Let's dive in. All right, first things first, before we can really appreciate the solution, we have to get a solid grip on the problem. And it's a problem that exists between pretty much every electrical source and whatever device you're trying to power. So let's start with a little thought experiment. I want you to picture 3 very different things: that little charger you plug your phone into, a sleek electric vehicle, and a massive wind turbine spinning on a hill. What on earth is the common thread that ties all of them together?
And the answer is conversion. Every single one of them has to change electricity from one form to another. Think about it. The AC power from your wall would absolutely destroy your phone's DC battery. The steady DC from an EV's battery can't directly spin its powerful AC motor. And the wild, fluctuating AC coming from a wind turbine is totally useless to our stable AC grid. You see, each one is speaking a different electrical language. That's the mismatch problem.
And this is where our field gets its definition. Power electronics is the art and science of solving this exact mismatch. It's all about taking electricity in whatever form it comes in, and then, with incredible efficiency and control, changing it into precisely the form that the load needs. It's not just a simple middleman. It is that brilliant translator we're talking about, making sure the source and the load can have a perfect conversation.
Okay, so let's jump into our first and probably the most common type of conversion you'll encounter. This is something you use every single day, turning the alternating current from your wall into the direct current that all your electronics need to survive. This job falls to a circuit called a rectifier. Now, I want you to think of AC electricity like a busy two-way street, where the current flows back and forth, back and forth. What a rectifier does is act like a set of one-way gates, forcing all that chaotic traffic to flow in only a single direction. It turns that two-way street into a one-way highway of DC power.
And you can actually see that transformation right here. On the input side, you've got that smooth, elegant sine wave of AC power from the outlet. The rectifier comes along and essentially just chops off the entire bottom half of that wave. So what you get on the output is this bumpy, pulsating DC. Sure, all the energy is flowing in one direction now, but it's not the smooth, stable power our sensitive electronics need just yet.
So how does this magic happen? Well, the real heroes are components called diodes. Those are the actual one-way electrical gates. Then you have capacitors, which act like tiny, super-fast water towers, storing and releasing energy to smooth out all those bumps in the DC voltage. And of course, you often have a transformer in there to step the voltage up or down to the right level to begin with.
Okay, so we've made some DC power. Fantastic. But there's another problem. It's almost never the exact voltage we need. For instance, a 12-volt car battery can't just be plugged into the computer chips that run the car. Those need a very specific 3.3 volts. This calls for another type of translation, which brings us to our second building block.
And that's the job of a DC to DC converter. If the rectifier was a set of one-way gates, you can think of a DC to DC converter as a super efficient electronic gearbox for electricity. It can take a DC voltage and shift it down, or even shift it up, to whatever precise level the load requires.
Now, one of the most clever designs for this is called the buck-boost converter. And its name tells you everything. It can either buck the voltage down to a lower level or boost it up to a higher one. It's incredibly flexible. Now, it does have a fascinating little quirk in its basic form. The output voltage is actually inverted or flipped upside down from the input. That's a key detail engineers have to account for. The secret to how this works so efficiently is all about high-speed switching. It's like a two-step dance. First, a switch closes, but the energy doesn't go to the load. Not yet. It gets stored in the magnetic field of a component called an inductor. Then, bam, the switch flicks open. That magnetic field collapses, and it releases all its stored energy to the load, but at a brand new voltage level. This whole dance happens thousands, sometimes millions of times every single second. It's incredible.
All right, now for the reverse. Let's flip the script. How do you run your AC-powered refrigerator from a DC battery during a blackout? Or how does a solar panel, which only produces DC power, feed that energy into the AC grid? Well, for that, we need our third type of circuit.
And that circuit is called an inverter. Just like the name implies, it does the exact opposite of a rectifier. It takes a steady one-way flow of DC and masterfully choreographs it back into the back-and-forth flow of AC. So, here's the amazing part. We start with a totally flat, constant DC voltage. The inverter then uses a set of incredibly fast switches to chop up that DC and piece it back together to look like a perfect sine wave, at exactly the right voltage and frequency we need.
But how can you possibly create a smooth, beautiful curve from a flat, boring DC line? The answer is one of the most elegant tricks in all of electrical engineering. It's called pulse width modulation, or PWM. Just imagine you're flicking a light switch on and off thousands of times a second. By precisely controlling how long the switch stays on versus off at each little pulse, making the pulses wider or narrower, you can create an average output that perfectly mimics a clean AC sine wave. This technique is the absolute heart of modern electric motor control and renewable energy.
Okay, we've covered the big three conversions, but there's one more piece of the puzzle. What if you already have AC power, but it's just not the right kind of AC? Maybe the voltage is wrong or the frequency is off. This brings us to our final category.
This is the domain of AC to AC converters. They do exactly what it sounds like. They take an incoming AC supply and they modify it. Sometimes it's as simple as changing its voltage, think of a standard light dimmer switch, but it can also be as complex as completely changing its frequency, which is crucial for things like controlling the speed of big motors.
So you've got two main flavors here. The simple one is an AC voltage controller. Again, your light dimmer is a perfect example. It just chops out little pieces of the AC wave to lower the total power. But then you have something like a cycloconverter. This thing is a beast. It can take AC power at one frequency, say 60 Hz from the grid, and directly synthesize a completely different, usually lower, frequency. This is how you get precision control over those massive, slow-moving motors you see in steel mills or giant mining equipment.
So there we have it. We've seen the four fundamental building blocks: rectifiers, DC to DC converters, inverters, and AC to AC converters. Now, let's just step back for a second and look at the big picture, because these aren't just abstract circuits in a textbook. They are the invisible backbone of our entire technological world.
So where are these translators hiding? Well, that tiny little power brick for your laptop, it's packed with them. The mind-blowing acceleration of an electric car, that's a high-power inverter and motor drive working in perfect sync. The fact that a windy day can help power your city, that's all thanks to power electronics cleaning up that messy wind energy for the grid. From the data centers running the internet to the trains we ride every day, this technology is the silent, essential engine of it all. It is, quite simply, everywhere.
And that brings us full circle. We've seen that power electronics is really the art of translation, of allowing completely different electrical systems to work together in harmony. Here's the key takeaway. Every single percentage point of efficiency we can squeeze out of these circuits has a huge ripple effect across our global energy use, saving power and unlocking new possibilities. So I'll leave you with this question to ponder. As our world demands ever smarter, smaller, and more efficient energy, what incredible new breakthroughs will the next generation of these universal translators unlock for us?